Hi everyone, here's Ray from UC Santa Barbara. I'm going to introduce about my work on empirical study of end-to-end video language transformers with masked visual modeling. This project is collaborated with Microsoft Azure AI. Large-scale pre-training has been widely adopted in text visual learning because of its promising performance gain on various downstream tasks. The architecture is usually as this: a cross-model transformer to fuse both vision and language modalities, and then support further tasks such as visual question answering, text or visual retrieval, and captioning. To learn from large-scale data, there are two most used training tasks, such as masked language modeling, aka MLM, and contrastive visual text matching, aka VTM. MLM is followed by BERT, which is to recover those missing word tokens and enhance the language understanding. VTM is another key step that learns to distinguish if a text-visual pair is aligned or not. This can help to bridge these two modalities and learn the fusion between each other. How about the visual part? Is there any way to enhance the visual modality just as MLM for language? Hence, we have masked visual modeling, aka MVM. Similar to masked language modeling, MVM also masks parts of visual data, and the model learns to recover those missing fragments. In this way, ideally, it can enhance its visual understanding just like language does. MVM has shown promising improvements in self-supervised visual pre-training, such as masked autoencoder, which recovers the raw pixels, or BAIT, which recovers the discrete visual tokens from vector quantization. Video MAE also extends MAE into videos, which also brings a great improvement. However, this similar technique seems not that effective on text-image pre-training. In this empirical study, it demonstrates that MVM even hurts the downstream performance. So for text video, how can we design effective MVM? Can it actually help for video and language learning? In this project, we conduct a comprehensive empirical study on masked visual modeling for video and language learning. We consider 8 targets for MVM, including low-level, semantic level, and multi-model guidance. For low-level features, we have pixel value following masked autoencoder and histogram of gradients, aka HOG. HOG is a traditional feature extractor which has a good performance on human face detection. It also brings performance gain on self-supervised visual pre-training. For semantic level, we have depth maps and optical flow as supervised schedule labels, and spatial focus image features from the image classifier, and temporal-aware video features from the video classifier. We also incorporate multi-model targets such as vector quantized visual tokens and multi-model features from clip image encoder. Our goal is to find the best MVM targets that can lead to the most improvement for video and language learning. We first take a look at MVM over text video data. Here we use web video, which contains 2.5 million text video pairs for pre-training. MVM from pixel can somehow benefit the pre-training, but the improvement is very limited. And for HOG, since they do not have the color information, it is unhelpful and even hurts the performance. Neither depth can be useful as MVM because it tends to separate the foreground and ignore the background information. Flow focus on the moving part between frames and will ignore the spatial details of static components. The optical flow estimation model also easily fails with the widely adopted sparse sampling strategy in end-to-end pre-training. Both SIF and TVF can lead to obvious improvements in text-to-video retrieval, but TVF fails to improve video question answering. Previous study also points out that existing benchmarks largely test on spatial understanding about the keyframe of the video, which limits TVF's effectiveness. The multimodal guidance, VQ, and NNF from clip can only slightly benefit only one task. VQ can help scene understanding by capturing the patch-level semantics and MMF can better contribute global similarity between the entire video and text sentence. So in summary, not all MVM targets can help video and language learning. Only Pixel and SIF can bring consistent improvement on both video question answering and text-to-video retrieval. Among them, SIF can gain the most significant advance. We try to combine useful MVM targets to have more improvements. However, the results demonstrate the joint of different MVMs is not encouraging. Pixel and SIF are the most two affected targets from the previous experiments. Pixel plus SIF performs better than Pixel only, but does not improve over using SIF alone. We hypothesize that the explicit details of Pixel values may conflict with the high-level visual semantics from SIF. Considering SIF with TVF, it seems not to bring a robust improvement, but it will result in excessive training overhead. So we chose SIF as our final pre-training settings. Because most pre-training will involve text-image data to help video and language, we also evaluate on the CC3M dataset. Unfortunately, MVM is not effective on text-image data. This findings is the same as the previous study, where current text-image pre-training usually does not consider MVM as the pre-training task. There are two reasons why MVM is not useful in this case. Firstly, it is challenging to recover missing fragments without visual implementations from neighbor frames, and the learning may be not visible. And further, MVM over images is trying to fit in a static frame, which can hurt the important video temporal. So we can see a huge downgrade on the retrieval task. From the above experiments, we find that it is not trivial to find a superior MVM combination. We adopt our best default settings using SIF as MVM for text-video data, and only VTM plus MLM for text-image data. We further go into the detail of the SIF target, where we consider features that are extracted from different image classifiers. Compare ResNet and Swing models, image classification accuracy is important. A better image classifier can usually provide more accurate visual features for MVM to learn, which benefits better visual understanding for video and language learning, while the downstream performance is not always positively correlated with the classification accuracy. We find that inductive bias is another key for MVM. Swing Large contains the highest image classification, but the improvement in text-to-video retrieval is not the best. Swing Base as SIF shares a similar feature dimension to our video encoder in the end-to-end transformer, which finally contributes the most performance gain. This suggests that the architecture design of both the target model and video encoder should be similar. From a global perspective, it is a trade-off between how informative this MVM target is and how feasible the model can learn from it. Even the features are informative, they may be difficult to learn, which cannot bring an additional improvement for the downstream tasks. We name our MVM settings SIF on video and none on image as Violet version 2 and compare it to previous SOTA methods. We gray out those methods that are pre-trained from significantly more data. With merely less pre-training data, 5 million from web video and CC, we even surpass Merlot or Violet, which are pre-trained from more than 100 million text visual pairs, by a significant improvement. This result indicates that MVM can be effective for video and language, and the design is crucial to the downstream performance, which is the core belief of our empirical study. A similar trend can be observed in text-to-video retrieval. Our Violet version 2 again achieves the best performance than all baselines that use the same amount of pre-training data, and even overpass all-in-one and our previous version of Violet. This further demonstrates that an effective MVM also benefits downstream text-to-video retrieval. In conclusion, we explored diverse MVN targets for video and language learning in this empirical study, including low-level, semantic level, and multimodal guidance. We consider various combinations of MVN over text video and text image data and figure out that SIF over video and none over image is the best settings. Going into detail, the features extractor is also important. The image classification accuracy is crucial but not always positively correlated. The similar inductive biases between the SIF extractor and the visual encoder is another key. There is a trade-off between informative learning and visible learning. We provide more studies on the training strategy, including the loss type, the masking ratio, and the masking strategy in our paper. Please visit this QR code to try our valid version 2, where we provide a bunch of checkpoints for all conducted settings in the paper for future research on video and language pre-training. Here's Ray from UC Santa Barbara. Thanks all for your listening.